Alrighty, howdy folks. Let's look at section 4 of chapter 14, and this is, as you can read, tangent planes and linear approximations. Okay, tangent planes. Ooh, that's a pretty big long statement. Let me read parts of it and then in fact graphically show you. Suppose a surface S has equation z equals f of xy, where f has continuous first partial derivatives, and let p of x sub 0, y sub 0, z sub 0 be a point on S. Okay, clear as mud? No, it should be fairly clear. So basically we have an xyz coordinate system, and we have a surface called S, and it's given by the equation z equals some function of x comma y. Does that look like a surface? I mean, if you want something touchy-feely in order to see what this surface is, take a printer paper and just curl it and hold it. So the surface, the curved surface of that printer paper is your surface, this z equals f of xy surface. Cool. And let p of x sub 0, y sub 0, z sub 0 be a point on that one. That's fairly straightforward to imagine, right? There's a point on this surface. So here it is. Okay, the next part. Curves c sub 1, c sub 2 or the intersection of planes y equals y sub 0, x equals x sub 0 with S. Let's see, what in the world does that mean? Curves even planes y equals y sub 0. Let's try to see what in the world a plane y equals y sub 0 means. Can you imagine what plane y equals y sub 0 is? Well, that is simply saying it's a plane parallel to the xz plane. So in this case, xz is a vertical plane. Would you agree? So a vertical plane that is parallel to the xz axis. Or imagine the best thing to do is imagine a plane that contains both the x-axis and the z-axis. Okay, that's an xz plane or the y plane because its normal is pointing in the y direction. We talked about this. Now, can you imagine scooting that vertical plane to y equals y sub 0? Well, it's a plane parallel to xz, and it is located at y equals y sub 0. Okay, now what you're supposed to imagine is such a plane intersecting this surface. Okay, so what I am expecting you to do sort of is hold a piece of paper, curve it in front of you, and maybe at the same level as your eyes. And now imagine cutting that plane, that paper, with a section, a vertical plane. And if you look from the side, you will see that in fact you have a curve where the plane cut the surface. That curve is what c sub 1 is. Cool? In the same way, you can imagine a plane x equals x sub 0. That means this plane is also vertical like the previous one. However, this is parallel to the yz plane. And where is it drawn? At an x value of x sub 0. Or the yz plane has been scooted to x equals x sub 0. And that also intersects the surface, and that intersects this surface along another curve called c sub 1. Can you imagine that? Well, if you cannot, or if you don't want to, too lazy, too bogged down with something else, some other homeworks, I figured so. So let me draw those things. Can you now imagine? So this is the c sub 1 curve. Would you agree with that? Is this the C sub 1 curve? Yeah, that's the one that's parallel to the xz plane, y equals y sub 0. And this is the one that's parallel to the yz plane. And so, yes, those are C sub 1 and C sub 2 respectively. So far, so good? Cool. Next. Lines T sub 1 and T sub 2 are tangents to these curves at P. If we have a curve, can we draw a tangent to the curve at any point on the curve? Yeah, we can draw a tangent. Now that's going to be a bit hard for me to draw and convince you that in fact it is tangential, but I'll give it a try. So to this curve C sub 1, we draw a tangent T sub 1 at this point P. And similarly to this curve C2, we will draw another tangent T2. Okay, what do they look like? Can you live with that? T sub 1, T sub 2? Thank you. Okay, now that we have drawn these tangent lines to those two curves, the next thing we need to know is the plane containing T1, T2. Can you imagine a plane that will actually contain T1 and T2? Yep, we talked about anytime you have two non-collinear lines, two lines that are not in the same line, and especially if we can put those two vectors together, in this case, instead of vectors, I'm talking about two tangent lines that do intersect and are not collinear. Yeah, we can imagine a plane that contains both the lines T1 and T2. That plane, ladies and gentlemen, is the tangential plane to the surface S at P. So that's the best I can do. All right, a lot of imagination has to happen from your side. But one thing I noticed is Americans are very good, because I guess you guys have grown up drawing all kinds of things right from childhood. You know, dad and mom would buy a whole bunch of crayons right from childhood, and you start coloring and all that stuff. So you have very good imagination and drawing skills compared to, most of us Indians, I think. Maybe the present generation of Indians is like you, but my generation, or at least let me speak for myself, I suck at drawing. I am pathetic at drawing. Pictionary. If I play Pictionary, my team is in trouble, especially when I have to draw. When I need to guess somebody else's, yeah, I'm okay. But if I have to draw, God forbid I'm asked to draw an elephant, that would look like I have no idea what the hell that is. Okay, enough about me. What the hell? Okay, so so tangential plane to a surface is the concept here. Okay, let's look at this. An equation of the tangent plane. Now that we know that there is a tangent plane to the surface z equals f of xy at the point, what's the equation of that? Apparently, it is z minus z sub 0 equals f sub x of x sub 0, y sub 0, rather evaluated at x sub 0, y sub 0 times x minus x sub 0 plus f sub y. What? What is f sub x? We talked about partial derivatives in the last section, right? So f sub x is partial of f with respect to x. And where do you evaluate that? At x0, y sub 0. X sub 0, y sub 0. Because we are looking at the point P, whose coordinates are x0, y0, z0. So we need to figure out the partial derivative f with respect to x at x sub 0, y sub 0. And multiply that by x minus x sub 0. Similarly, partial f with respect to y evaluated at the same point times y minus y0. And z minus z sub 0 is equal to that. Ta-da! That's the equation of the tangent plane. Does that make any sense? Well, let's see. It kind of should. For what reasons? Well, let me think about a good way to explain. Yeah. Do you remember the slope point form in 2 dimensions? What's that? Y minus y1 equals m times x minus x1, right? Or y minus y0 is equal to m times x minus x sub 0. What is m? Oh, the slope of the tangent line, or the slope of the line, because we are talking, there's no tangent here. Because we are talking about a line, the slope of the line itself is m. Oh, the equation of a line is y minus y sub 0 is equal to m times x minus x sub 0. Does this have a similar form? Instead of y minus y0, do we have a z minus z sub 0? Yeah, and m is the what? The slope of the line. Well, here the slope, is that the same as the partial derivative? Does the derivative give you the slope of a tangent? Yeah, because we are looking at the tangent plane, or in 2D, a tangent line, yeah, that's the derivative evaluated. That should give you the slope. However, because this is two-dimensional, we have to account for the other tangent line, that is with respect to which I better be careful. If sub x, yeah, when we find f sub x, I think that's a better way to explain. When we find f sub x, partial f with respect to x, what do? We let y equal a constant, right? We allow y to be a constant. In this case, that constant is not just some constant, it is a specific constant, y equals y sub 0. So we are talking about the y equals y0 plane cutting the surface, that C1 curve, and this represents the tangent, that tangent t sub 1. Okay, and and so what happens, since y equals y sub 0, this stuff just goes to 0 if we are talking about y equals y sub 0. However, if we hold x constant as we find partial f with respect to y, and specifically x equals x sub 0, this term disappears and we end up with this tangent line. Okay, so we have a combination of the two, a nice linear combination of the two. So that is going to be the equation of the tangent plane to the surface. All right. To understand this better, I'm trying to say, recall whatever I said. If you have a y equals f of x, what do? We draw a tangent at this x equals a, and then we use that. We, given the curve at point a f of a, equation of the tangent line at this one. In our case, it's a tangent surface, but in the case of 2D, we have a tangent line, and that is nothing but y minus y1 equals m times x minus x1, where m is nothing but the derivative, f prime of a, derivative of the derivative of the curve, which is f prime of a, right? And y1 is nothing but f of a. And so y equals f of a plus f prime of a times x minus a. Okay, let's see what I said here. In fact, this is the concept behind linearization of a function. We studied linearization in Cal 1. Okay. For instance, though y equals f of x represents a curve, we can approximate the curve as a straight line near the point x equals a. Okay, if this is the idea, the curve y equals f of x is a pretty curvy thing. There's no doubt about that. Whereas this tangent line is just a straight line. Are you trying to tell me that this tangent line and this curve are the same? If I did, then I would be very wrong. However, I don't know. Unfortunately, I cannot zoom in. But if we were to take only, say, the itty bitty portion of this curve, just that little piece of the curve. Now, how bad is this line as an approximation of that curve? Not bad at all. So as long as we're talking about being very close to the point where we drew the tangent, that tangent is a pretty decent approximation of the curve within a very small neighborhood, of course. That's the whole idea. That's when we say we have linearized the function at that point. We have made a curvy thing into a line, approximately. That's the point of linearization. And we write the linearization of x is nothing but f of a plus f prime of a times x minus a. We are approximating by the tangent line. Now, in this case, in the three-dimension case, or 3 case, similarly, a surface z equals f of xy, z equals f of xy is a surface. We can linearize the surface just as we linearize the curve, and we can write L of x comma y is f of ab plus f sub x of ab times x minus a plus f sub y ab times y minus b. Okay, this is a linearization of it. This is the concept that you really need to grasp in this section. Okay, folks? All right. Definition. One more thing. If z equals f of xy, then f is differentiable at ab if we can find delta z and write it in the form of f sub x a sub b evaluated at ab times delta x plus f sub y ab times delta y plus some epsilon 1 delta x plus some other epsilon 2 times delta y. What the hell is this talking about? I'll explain in just a second. Delta z. Can you imagine what delta z actually represents? It represents change in z. Change in z when what? Let's say you know the function's value at ab. Okay, at x equals a, y equals b, you know the z value. Z equals f of ab. Now, if you go slightly delta x away from that AB in the x direction, so that is you have a plus delta x, and also change y by delta y, b plus delta y. You are at a different point now, right? Delta x away from a, delta y away from b. There you have a different point. At that point, the z value would be different. The z value would have changed. How much is the change in z? That is delta z. And delta z is definitely equal to the partial derivative a with respect to b times delta x and all of this, plus, because we are approximating the actual surface with a tangential plane, well, the actual surface is not just a simple plane, so there would be an error, and to account for that change away from the planar nature of this tangential thing, we will add epsilon 1 times delta x and epsilon 2 times delta y. Okay, now the crucial thing here is, as delta x and delta y approach 0, That means they get very, very small. The change in x and change in y is very, very small. Then these multiplying factors, epsilon 1 and epsilon 2, they also get very close to 0. That's the point that this is making. Okay. Now, if you didn't understand that, let me illustrate this with the okay, I think I do have this. So let me illustrate that with 2 dimensions, so you will actually gain a much better understanding of it. If the partial derivatives f sub x, f sub y exist near AB and are continuous at AB, then f is differentiable at AB. Okay. Now, that's a theorem. So what does the theorem say? If the partial derivatives must exist near A and B and must be continuous at AB, then we can confidently say that f is differentiable at AB. Okay. Oh, differentiable. Ooh, differentiable back in R2 was something else, wasn't it? We said a function f is differentiable at A if that limit of a plus h minus f of a over h as h approaches 0, that limit exists, we would say, yep, the function is differentiable at the point. Here, we define it slightly differently. If the partial derivatives exist and are continuous at AB, then f is differentiable at AB. Okay. When it comes to differentials, what's the difference between delta z or delta y and dy? Okay, that's what I'm planning to show you. Back in 2D, when we have some curve y equals f of x, and we are at a point x and f of x, okay, and we go to another point where the difference in the x coordinates between those two things is delta x. X plus delta x is the x coordinate of this point. That is, the x value has changed by delta x as we moved from this point to that point. Let me repeat that. Our original point is x. Then we looked at another point. The change in x value as we go from one point to the other point is delta x. Okay, if that is the case, what should be the change along the y direction? Well, that should be delta y. Right? As we go, what is the difference in the y values between the 2 points? Delta y. Just as the difference in x value between the 2 points is delta x. The thing is, delta x and dx are exactly the same. However, delta y and dy are not the same. dy is the differential. What's this dy then? Well, if you draw a tangent at this x f of x at that point, and you measure the change along the tangent, that is your differential dy. Cool? Same concept applies here. Y equals f of x and dy is nothing but f prime of x dx. If you did u substitution, I'm sure you remember u equals x square. What is du? Or 2x du is 2x dx, you would say. Where did that come from? From this concept. Y equals f of x. What is dy? F prime of x dx. If I say y equals x square, what is dy? 2x dx. That's the idea. Okay. All right. Now, similarly, for multivariable functions, we have what is called a total differential. That means if we have z equals f of xy and we want to look at dz, not the exact change in z, delta z, but the differential dz. It's a total differential dz. How do you find that? Well, partial z with respect to x times dx plus partial z with respect to y dy. That is the total differential. That is, please Please pay attention to this. In light of what this dy was what? The change in y along the tangent line, not the actual change in y. In the same way, dz is not the actual change in z, but the change along the tangential plane. How do you find that? Well, it's a combination of the change along the x-axis, along the x direction, plus the change in the y direction along the tangential plane. So that's why whatever the derivative is times dx, that part is similar to f prime of x dx. But the thing is, if there were to be no change in x, doesn't necessarily mean there is no change in z. Z could be changing because y is changing. So we have to account for that as well. And that's why we slap in this extra partial z with respect to y dy. Okay. Boy, that figure, you draw a tangent plane and then go to another plane, that looks awfully confusing. But if you can imagine it yourself, that would be great, especially by looking at the first thing that I drew in the very first slide. Take a look at that and see if you can traverse from that point P a little bit in the x direction, by delta x in the x direction and by delta y in the y direction, and locate that point, what the z point is, along the tangential plane. That's what we are talking about as dz. Okay. I think that's about what I can cover as a theoretical part, and let's work some problems. Simple problems, straightforward ones. I hope you don't feel that I'm insulting your intelligence by doing this. Find an equation of the tangent plane to z equals blah blah. Okay. Do we remember I mentioned this is z minus z sub 0 is equal to partial f with respect to x at x sub 0, y sub 0 times x minus x sub 0, this thing. Well, do we have all the information to be able to figure out all this? Z, that's what we need to find. Do we know z sub 0? That's the z coordinate of the point, well, which happens to be 3. So that we know. F sub x. Do we know f sub x? What is that? Partial f with respect to x. Well, this z equals, isn't that the f of xy? So the question then becomes, when we know that the f of xy is this guy, x plus 2 to the 1 square minus 2 times all that, can we take the partial derivative with respect to x? Yeah. Can we evaluate it at x0, y0? What are x0, y0? The x and y coordinates of the point, that is 2, 3. Okay, x sub 0 is 2, y sub 0 is 3. X minus x sub 0. What is x? Just leave it as x. X sub 0, we already talked about it. Similarly, this point. So I think this is just a straightforward plug and chug kind of a thing. We identify that f of xy is this, blah, blah. x0, y0 is that. F sub x. Can you take the partial derivative of this with respect to x? Yep, this is 2 times x plus 2 times the derivative of x plus 2 is just 1, so 2 times x plus 2. The derivative of this goes to 0 because partial we will hold y as a constant, and so partial with respect to x would be 0. The derivative of this is 0, and so partial f with respect to x is simply 2 times x plus 2. Partial f with respect to y, negative 4 times y minus 1, right? This would go to 0. The derivative of this goes to 0, and so we got that. Can we evaluate these at 2, 3? Yep. -8, 8 and -8. So plug and chug. Z minus Z sub 0 is 3, 8 times x minus 2. Okay, so Z equals 8x minus 8y plus 11. That's it. Is that all, man? Yeah, man, that's it. I think I got tempted to try this out in GeoGebra. I wanted to see how it looks, and man, it's a bit of a mess. Do I have it? Yeah, that's kind of how it looks. I think I still have this open. Yeah, boy, isn't that confusing. So the red thing is the actual surface. It's pretty complicated looking thing, and that green thing, that's the tangential plane. So if I turn that off, so the point 233 is located there on the surface, and if I turn the tangent on, that's what it looks like. Let me see if I can turn the plane itself off. Yeah, so that plane, is that tangential to the surface there? Yep, it is. Okay, somehow not such a clear one, but it's there, and you have the ability to draw planes like this, surfaces like this, and planes and all kinds of things. So as you can see, all I did is simply typed up that x minus blah 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 is equal to z equals blah 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 kind of a thing, and that created the surface. And I said a equals 2 comma 3 comma 3, that's our point. I should have said p maybe. And then the tangential planes equation, I just typed 8x minus 8y minus z equals -11, or maybe I said plus 11 equals 0. That's it. It drew the whole thing for us. Okay, that's what you see here. What else? Okay, let's look at another problem. Explain why the function is differentiable at the given point. Then find the linearization of L of x of the function at the point. I like this one because I'll show you if you're wondering, why do you care about this stupid linearization, man? You'll see. F of xy is equal to square root of xy, right? And at 1, 4. The theorem said, if the partial derivatives f sub x and f sub y exist near AB and are continuous at AB, then f is differentiable at AB. So the differentiability seems to hinge on the f sub x at AB and f sub y at AB. So let's go ahead and figure those things out. Given that f of xy is square root of xy, would you agree the partial derivative of xy would be 1 over 2 times square root of xy times, we have the chain rule, we have to differentiate xy with respect to x, which gives us just y, right? Y is a constant. Y times the derivative of x is 1. So if we simplify this, this becomes 1/2 square root of y over x. What? How'd you get that, man? Well, is there a square root of y here? And is there a y? Can you think of it as square root of y, the quantity square? So one of the square root of y's cancels out with one of the square root of y's, leaving you with a square root of y on the top. Okay, that's one way. Or can you say y a to the m over a to the n is a to the m minus n? So y over y to the 1/2 is y to the 1 minus 1/2 is y to the 1/2 is square root of y. What? I don't know what you said, man. Yeah, rewind and watch it. Similarly, if we find f sub y, 1/2 square root of x over y. So the question is, what's f sub x at 1, 4? Plug and chug, turns out to be 1. What's f(x) turns out to be 1/4. So were we able to figure out f sub x at 1, 4 and f sub y at 1, 4? Yep. Is this are these continuous for all positive values of x and y? As long as both x and y are positive, right, so these things are okay. And clearly near 1, 4, there is a surrounding neighborhood of it where x and y are positive. So guess what? This is differentiable at 1, 4. Okay. Now, since the linearization of the surface at AB is linearization, so we are done with the first part. Now let's look at the linearization. That thing we remember is f of a comma b plus f sub x of ab, f sub x evaluated at ab times x minus a, that thing, right? So that simply becomes f of a comma b. Did we ever figure out f of ab? No. Let's plug 1 and 4 for x and y to figure out f of 1 comma 4, and that turns out to be square root of 4, which is 2. That's what I have here. Plus f sub x at 1, 4, we figured that out. So times x minus x1, times x minus 1 and plus 1/4. You cool about this? It's a fairly straightforward problem. Take a good look at this. Next, let's look at, in the previous problem, we saw that f of xy, as promised, why do we need this stupid linearization, man? We need this because of this. Check this out. Was the original function square root of xy? And was the linearization this? Okay, now find f of 1 comma 4. And also find f of 1.1 comma 4.1. That means don't go too far away. That means don't make delta x and delta y too large. Delta x and delta y? Yeah, delta x is, as we go from 1.4 to 1.1, 4.1, have we gone to a different point? Now, didn't I say that delta x is the change in the x coordinate? Yeah, so 1 and to 1.1, the change in x is 0.1. Similarly, change in y, delta y is 0.1. Right? So as long as you do not make your delta x and delta y really large, let's see what this linearization does. So let's do, without much further ado, let's figure out f of 1, 4, both with the original function, that is square root of xy. Plug 1 times 4 is 2. Now, what is L of 1 comma 4? Let's go to the linearized version of it. Hey, that also turned out to be the same value too. Exactly the same. There's no difference whatsoever. Duh, man. That's ridiculous. Being excited about that is ridiculous, because this was x minus a, and x equals a here. So a minus a is 0. Yeah, of course. And this was f of ab. It's not a surprise that this turned out to be, these two values turned out to be the same. But the next one is pretty interesting. The actual value of f of 1.14.1 is square root of 1.1 times 4.1, turns out to be 2.12368. Okay, now on the other hand, if we use the linearized one, so we go here, and that turns out to be 2.125. Can you live with that? Would you say 2.125 is pretty close to 2.12368? That's the idea. Okay, what's the big deal? It was so easy to. No, no, no. Whoa, 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 whoa. If you are saying to me, come on, man, what's the big deal about this? The big deal is this. Let's say we are talking about some, not just a square root of xy, which we can punch into calculator fairly easily. What if we are looking at, say, ninth root of xy? Ninth root of xy at some particular number may be somewhat straightforward. We can figure it out. But if you go slightly away from that, and how would you find that? That would be difficult in especially those days when we didn't have computers and calculators. So this says, don't worry. You can just use this linearized version and you won't be way too off, especially if you make your delta x and delta y to be kind of really small. Then what you get here by linearized version is almost the same, is pretty approximately close to the actual value. Still don't think that's a big deal? Okay. Now, the beauty of this is all of this is preparing you for solutions of partial differential equations. You will learn, just as I don't know if you already had differential equations or not. Differential equations sometimes tend to be very hard to solve. And partial differential equations tend to be sometimes even harder. So at that time, what we do is we would know the value at some particular point. So our objective is to keep on finding the solution at every point. So what we do is, hey, I know the solution should be this specific number at this point xy. Okay, using that, can I scoot by just a tiny amount delta x and delta y and figure out using this linearization what the value is at that new point? Yeah, good. So now we know the solution at 2 points. Okay, now that we know the solution at the second point, could we use that value and figure out a delta x and delta y away from that point? And keep marching forward like that so that we know the solution at just about every point on the surface. That is what this is absolutely helpful for. Okay, so beautiful concept. And also, I went ahead and figured out what the percent error was. How do you figure a percent error? The actual value, the absolute value of actual value minus, this is the actual value, minus the approximate value divided by the actual value times 100. And that turns out to be 0.062%. Boy, for engineers, an error of 0.062% is very, very tiny. You would gladly take it. Okay, that's the idea. And I think I have another example, a similar thing. F of xy equals y plus sine of xy 0, 3, find the differentiable, blah, blah. The only difference is maybe the functions are just a tad harder than the previous one to differentiate. Here is how it turns out to be. And I evaluated f sub x and f sub y at those points, and because f sub x and f sub y are continuous for all values of x and y not equal to 0, but as long as x is not equal to x and y are both not 0, can I have yeah, for all values of x, no, I think no, x can be 0. That's not an issue here. As long as y is not equal to 0, because it's in the denominator. So for all values of x and for y not equal to 0, y can take on any value as long as it's not equal to 0. Thus the function is differentiable at 0, 3. Cool. And linearization, just plug and chug. Okay. Now ask yourself, if we needed to do the similar thing, can you figure out f of 0.1 and 3.1? 0.1 and 3.1. So that means sine of 0.1 over 3.1, sine of 1 over 31. Man, sine of 1 over 31. What in the world is that? You cannot figure out sine of 1 over 31, right? But not to worry. We can use the linearization and get that value fairly close. All right, folks. So that's about this section.